Okay. So for this standard, um, we're looking at two different theorems and looking at some of the applications of those two theorems. These are two theorems that in the AP curriculum you are expected to know and be comfortable with and how to use them. Both of them relate to special cases of instantaneous rate of change, the derivatives. So we've been working with integration for a while, so this standard goes back to working with a little bit of derivative stuff. If you think back a few units to when we talked about the intermediate value theorem, this will feel similar. Because when we talked about the intermediate value theorem, that was an existence theorem. Well, Rolle's theorem and the mean value theorem are existence theorems. So they don't tell you how to solve for the wanted value, but they either demonstrate or guarantee a situation to be true. And it'll make sense after we talk about it. It'll make sense just logically that these things would be true, but as if you think back to geometry, when you did proofs, some stuff was very like the reflexive property. Of course, this line would equal this line because they're the same line, but you still have to state it as a theorem. So that kind of is what happens here. It makes sense in our mind that it would work out that way, but we still have to state it as a theorem. All right, since Rolle's theorem is a special case of the mean value theorem, we're going to start by addressing the MVT. So, mean value theorem. Mean value, average. So, average is going to be a part here. Now, the mean value theorem we have to be careful with because there's a mean value theorem for integration, which is like the average value stuff that we talked about yesterday. But the mean value theorem just focuses on derivatives because it basically states that if a function is continuous, there's no breaks, and differentiable meaning there's no cusps or vertical tangent lines. So if it's continuous and differentiable between two endpoints, A and B, then we can say, okay, there has to be, it's guaranteed, that there's at least one value between A and B, we're going to call it C, where the instantaneous rate of change there, at C, is equal to the average rate of change. Okay? If you think of it in terms of graphs, then we could say that if a function is continuous and differentiable between two endpoints, those are the stipulations that mean that this is going to happen, then the slope of the tangent line, because tangent lines are connected to instantaneous rates, that will be equal to the slope of the secant line. And a secant line is a line that just connects 2 points, so that's talking about average rate of change. So for a graph, it might make a little more sense when you look at it in terms of a graph. You have these two endpoints, A and B. You have this function, this curve that's drawn in, and maybe I should draw it with a different color. Okay, so you have this function here. And then you have these two cutoffs. So the secant line is this line right here because it's the line that connects both the 2 points that cross your A and B. That would be considered my average rate of change because you have a y value here and a y value here, and then the average rate of change's slope would be the slope of that line. Now what this is saying is no matter what the curve looks like, if it's continuous and differentiable, so there's no cusps or vertical tangent lines, then it has to be true that at some x value on this curve, at some c along this curve, whatever the slope of the secant line will match the slope of a tangent line. So if you know the secant line is this slope, you can kind of eyeball where that would be. Where if I draw in a tangent line at this spot here, the slope of that tangent line would match up with the slope of the secant line. So all the mean value theorem states is that this is going to be true. That if it's continuous and differentiable, that there is at least one spot in between A and B where the average rate of change is equal to the instantaneous rate of change. Okay? So using the MVT, because this is the existence theorem, it just says that this is going to be true if you're continuous and differentiable. if you're asked to use the mean value theorem to find a C value, to find that one value that gives me the instantaneous equal to the average, then you're using this following setup to solve. You're trying to find the instantaneous rate of change at some C, and you're setting it equal to the average rate of change. Because this would be like if you're finding slope, the difference of our y values divided by the difference in our x values. So this is the setup that we would use to solve for where that C value actually is. Okay. Now, we have two examples we're going to talk through with this concept. So, example 1. Given this function, find all C values in -1 to 1, such that the slope of the tangent line at that C value is equal to the slope of the secant line. So this is saying find where the instantaneous rate of change is equal to the average rate of change. Well, I know it has to be there somewhere because this is a polynomial. And polynomials are continuous and differentiable. This is going to be a nice, smooth curve. So to set up the problem, excuse me, and maybe we should just show that we at least thought about the fact that polynomials are continuous and differentiable. And when we were talking about existence theorems before, the reason that we talked about them is because it doesn't help us solve it, like we have to do other stuff to solve for it, but it at least guarantees that it's going to be there in the end. So we know we're going to get to an answer. Alright, so polynomials are continuous and differentiable, meaning this is going to end up having an answer when we solve. Now, I'm going to find the slope of the secant line first, because I'm looking for where the derivative at that C value, whatever that C is equal to your average rate of change. So where the derivative is, I have the function. I don't have the C, but I have the function. So I'm going to take the derivative of that function. So we have 3x squared minus 2x minus 2. And I'm going to set it equal to my average rate of change. Well, my average rate of change is going to be f of 1 minus f of -1 all over 1 minus -1. So if I punch that out, if I plug in 1, I get 1 minus 1 minus 2. So I get -2. F of -1, if I plug in -1, I get -1 minus 1, so that's -2, plus 2, so 0. And on the bottom, I get 1 plus 1, so 2. So if I simplify that, I would get -1. Okay, so my average rate of change is -1. And then I'm going to solve it. I have a quadratic, so I can either use the quadratic formula or I might be able to factor it. I'm going to add 1 to both sides. And this one is factorable, but I'm going to use the quadratic formula. So x is going to equal 2 plus or minus square root of 4 minus 4 times 3 times -1 all over 2 times 3. So we get 2 plus or minus 4 plus 12, so 16 over 6. So I get 2 plus 4 divided by 6, which is 1, and 2 minus 4 divided by 6, which is -1/3. So actually, both of these values end up working. I get two answers here because both of these values are in my domain. Now, if this was a parenthesis instead of a bracket, then -1/3 would technically be my only answer because 1 would not be included. But these are all the C values that actually at 1 and at -1/3, my tangent line would be equal to negative 1. Okay, so another problem that's a little bit different because it's going to be a story problem, but gets to the same concept. So a company introduces a new product for which the number of units sold is this expression. So number of units sold is equal to all this stuff where T is in months. And actually, for the sake of this problem, because I would hope you would do this anyway, I'm going to simplify this function for us. So I'm going to distribute the 200 through. So you get 1,000, and then 200 times 9 is 1,800. Okay. I'm going to have to change this wording here. Actually, that's what it would be asking. So we're going to find the average rate of change of S of T for the first year. So, to do that, we're going to take the derivative. So, not derivative. Average rate of change is this expression that we had up here, the f of b minus f of a over b minus a. So, s of b minus s of a all over b minus a. Plugging in, for first year, that's going to be from 0 to 12. So I'm going to put the function in my calculator here. So 1,000 minus 1,800 divided by 2 plus t, or 2 plus x. Go to my table. If I plug in 0, I get 100. If I plug in 12, I get 871.43. So we have 871.43 minus 100 all over 12 minus 0, or 12. So if I subtract 871 minus 0.43, if I subtract 100 from that, divide by 12, I get 64.286. So average rate of units sold. Okay, so then we're supposed to find what month does S prime of t equal the average value. So I have to take the derivative of my function. The derivative of 1,000 is 0. And then I'm going to have to use the quotient rule here, or I can bring this up to the top, and that might be easier. So my S of t is 1,000 minus 1,800, and I'm going to bring that 2 plus t up. S prime of t then is going to be 0, and pull the negative 1 up front. So I have 1,800 times 2 plus t to the negative 2 times 1, because I'm using the chain rule there. Alright, so we're going to set S prime of t, so that expression, equal to 64.286, since that's my average, and solve from there. So we have 1,800 over 2 plus t squared equals 64.286. I'm going to go ahead and cross multiply here to get my t in the numerator. Whoops. Divide 1,800 by 64.286, and I get 2 plus t squared equals 27.999, and then I'm going to take the square root of both sides, and I get 2 plus t equals 5.291, and then subtract. So you get 3.291. So third month is in March. Since t is in terms of months, and we're looking for what month average equals the instantaneous. All right, so Rolle's theorem. Rolle's theorem is just a special case of the mean value theorem. In the Rolle's theorem, the average rate of change ends up being 0 because your y values at your endpoints here end up being equal. So when you're finding a c value where the instantaneous rate of change equals the average rate of change, your tangent line ends up being horizontal. And that's because if you have the same y value at your endpoints, the secant line that connects them is going to be horizontal. So if you're looking for a tangent line, that's my curve. If you're looking for a tangent line, then your tangent line would have to be also horizontal. Well, that only happens at maxes or mins. And so that's why this is a special case, because sometimes the Rolle's theorem is used to find max or mins in a range of values. All right, so we're going to do one example using the Rolle's theorem, but it's going to be very similar to how to set up the mean value theorem. If you let f of x equal that function, so it's continuous and differentiable, because it's a polynomial still, we're going to find all values of c in 1 to 4 such that your instantaneous rate of change equals 0. So, if I wanted to guarantee that I was going to get an answer, all I'd have to check and make sure is that if I plug in 4 and I plug in 1, I get the same y value. And so I'm going to just double check that, because then it is guaranteed that I would get an answer. Okay, so in this case, I get 0 for both my y values. That's not going to happen, but if I got a 3 and a 3, all I need to make sure to guarantee that this is going to be solvable using the Rolle's theorem is that your endpoints end up having the same y value. So same y value, Rolle's theorem applies. Okay? And that just guarantees that we're going to get an answer. That's not how we solve it, but that's just guaranteeing that we will be able to solve it. So now we do the same thing that we kind of did before. You're going to take your derivative. So we have to find the derivative of your expression there. And you're going to set it equal to 0. Because derivative is instantaneous rate of change. And so we're looking for the x value that will give me a derivative or rate of change value of 0. And that means a horizontal tangent line. I can add 5, divide by 2, and I get 5 halves. Excuse me. 2.5 is in that interval, so that is my c value. And I only have one spot where that's going to happen, where I have a horizontal tangent line in there. So to recap, these theorems tell you a certain c value will exist if certain qualifiers are in place. The qualifiers for existence of the mean value theorem are that the function has to be continuous and differentiable. And if that happens, your average, you will be able to find a spot where your average will equal an instantaneous rate of change. The Rolle's theorem goes one more step and adds in the requirement that if f of a equals f of b, so if your y values of your endpoints are equal, then there's a c that guarantees you're going to have a horizontal tangent line at that point. Now, in your practice for this, your practice work is going to be pretty important for this theorem stuff, because that's where you're going to see the application, or how they actually use the Rolle's theorem and mean value theorem to find values, such as, like, for example, 2, that was a pretty straightforward case of using the MBT idea to find where the average equals the instantaneous. So that's it for standard T1.